All right, question number 1 of the stoichiometry review says write the complete balanced equation for the following reactions. So letter A says HCl plus AlOH3 produces AlCl3 plus H2O. So just simply starting out here, I see 1 hydrogen plus I see 3 more there. That makes a total of 4. So I'm going to put a 2 right there. Okay, and then I go to the next element, chlorine. There's 1 chlorine here. There are 3 chlorines here. So that means I need a 3 right there. Now, by fixing the chlorines, I mess up the hydrogens, so that now makes the hydrogens have 3 hydrogens, plus again the 3 from here makes 6 hydrogens, which means that 2 needs to turn into a 3. And then we've got 1 aluminum, that's balanced. And remember, the 3 outside the parentheses goes to the hydrogen here, but it also goes to the oxygen. So that's 3 oxygens, and there's 3 oxygens. So that equation is now balanced. So it's 3 HCl's plus AlOH3 makes AlCl3 plus 3 H2O's. Letter B, Na3PO4 plus MgSO4 makes Na2SO4 plus Mg3PO42. Now in this case, we start with 3 sodiums and 2 sodiums. So we need to get to a number that is consistent between the 2 of them. So the smallest number that 3 and 2 both go into is 6. So to get this sodium here up to 6, we're going to put a 2 right there. And to get this sodium up to 6, we're going to put a 3 right there. And that makes 6 sodiums on both sides. Okay, and again, that 2 goes to the Na3. It also goes to the PO4. So there's 2 PO4s and there's 2 PO4s. So the PO4s are balanced. And then we've got 1 magnesium here. Here we have 3. So I need to put a 3 right there. And again, that 3 goes to the magnesium. It also goes to, oops, too far. It also goes to the sulfate. And again, this 3 for the sodium also goes to the sulfate. So there are 3 sulfates on both sides, which means this equation is now balanced. Letter C says FeO plus O2 makes Fe2O3. So we've got 1 iron. Here we have 2. So I'm going to put a 2 right there. That makes 2 oxygens plus 2 more is 4. And over on this side we have 3. So we've got 4 on one side, 3 on the other. The only thing we can do there is we got to make this number bigger. So instead of 1 Fe2O3, we're going to make 2 Fe2O3s. And now I realize that gives us too many oxygens, but again, we'll figure that out here in a second. Okay, because now with a 2 in front of here, now there are, because this is a 2 right here, that makes 4 irons all total on the right hand side. So over here on our reactant side, we need to put 4 irons as well. And again, that 4 goes to the Fe and to the O. So that is 4 oxygens plus 2 more oxygens is 6 oxygens. And hey, what do you know? 2 times 3, 6 oxygens. That equation is now balanced. Okay, and then letter D says butane gas, which is C4H10, completely combusts in oxygen gas. Oxygen gas, as we've seen many, many times in this class, is O2, producing carbon dioxide, CO2, and water, H2O. Now we've got 4 carbons on the left, so we need 4 carbons on the right. We've got 10 hydrogens on the left. I'm going to put a 5 there, and that makes 10 hydrogens on the right. And now in terms of oxygen, here I have 2. 4 times 2 is 8, so there's 8 oxygens, plus another 5. I've got 13 all total on the right-hand side. But again, here I have to have an even number because it's O2. which means I have that, what we've called that odd-even problem. So the way to solve that is go back to the very beginning and double everything. So the 2 goes there. This 4 that was here becomes an 8. The 5 becomes a 10. And now we've got 8 times 2, 16, plus another 10 oxygens is 26 oxygens. So I put a 13 right there, and now it is balanced. All right, let's continue here. That is all for number 1. Number 2 says, using each of the balance equations above, answer the following questions. Now, part A on number 2 goes with the balance equation from part A. So we're going to use part A in number 1 to help us with part A in number 2. It says, what mass of AlCl3 is produced when 62.4 grams of HCl reacts with excess AlOH3? So in this case, we know that we have 62.4 grams of HCl, which is, again, this, and we need to figure out how much AlCl3 it's going to make. Okay, and it tells us that we have excess AlOH3, so that's our excess reactant, so we don't have to worry about the AlOH3 at all. So they only give us one number, so let's just start with that number, 62.4 grams of HCl, and then we've got to convert grams to moles, so we're going to use the molar mass of HCl from the periodic table. Chlorine's 35.5, hydrogen is 1, that's 36.5 grams in 1 mole of HCl, and now I go to my balanced equation. 3 moles of HCl is going to make 1 mole of AlCl3. And again, I know to use HCl on the bottom because that's what's given up here, and I know to get AlCl3 on the top because that's what they're asking us about in the question. And now my last step is I need to convert my moles of AlCl3 to grams. And so to do that, I'm going to take 35.5, I'm going to multiply it by 3 because there's 3 chlorines, and then I'm going to add the mass of aluminum, which is 27, which gives me a molar mass of 133.5. Okay, and that's the number of grams, again, in 1 mole. So in 1 mole of AlCl3, there are 133.5 grams. So 62.4 divided by 36.5 divided by 3 times 133.5 equals, with 3 significant figures, 76.1 grams of AlCl3. Okay, part B says how many moles of MgSO4 are necessary to produce 43.5 grams of Mg3PO42 and excess Na3PO4. So again, think about, what are they asking us about? They're asking us about MgSO4. So we're trying to find this, and they're giving us information about this. So we need to go from this back to this. So the only number that they give us is 43.5. So we're going to take 43.5 grams of Mg3PO42, and again, anytime you have grams, the only thing you can do is convert to moles. So I need the molar mass of Mg3PO42. So magnesium's 24.3, and there's 3 of them, so I'm going to times it by 3. Plus phosphorus is 31, and there's 2 of them. So plus 31 times 2. And then oxygen is 16, and there's 4 of them, but then there's 2 of those. So there's 8 oxygens all total. So that's plus 16 times 8 equals 262.9 grams in 1 mole of Mg3PO42. Okay, and now I've got moles of Mg3PO42, so those have to go on the bottom, Mg3PO42 on the bottom. And on top, I'm going to put moles of whatever they're asking about. So again, reading the question again in 2b, how many moles of MgSO4? So moles of MgSO4. Now I go to my balanced equation. In front of Mg3PO42, there's nothing, so that's a 1. In front of MgSO4, there's a 3, so that goes there. And notice they're only asking for the moles of MgSO4. Well, I've got moles of MgSO4 right here, so I'm done. I don't have to do anything else. So now I just need to take the numbers that are in my equation, 43.5, divide by 262.9, multiply by 3, and then I've got 3 significant figures here, so that's going to be 0.496 moles of MgSO4. Okay, so 0.496. Okay, part C says what mass of O2 is needed to completely react with 22.7 grams of FeO. So again, 22.7 grams of FeO. Molar mass of FeO is 55.8 plus 16, which is 71.8 grams in 1 mole of FeO. And now I can go moles, whatever's up here, remember, has to come down here. Moles of FeO to moles of, now at this point, I don't know, I got to read the question again. 2C, they're asking about O2, so I'm going to go to moles of O2. And then from my balanced equation, it looks like 4 moles of FeO reacts with 1 mole of O2. And again, they want the mass, so we can't stop at moles this time like we just did on B. Now we got to go back to grams like on A. Oxygen has a molar mass of 16. There's 2 of them. That's 32 grams. So 22.7 divided by 71.8 divided by 4 times 32 is exactly how I'm typing it into my calculator, and I get 2.53 grams of O2. Okay, and then the last one in number 2, calculate the mass of carbon dioxide when 0.125 grams of butane reacts with excess oxygen gas. So we're going to take 0.125 grams of butane, C4H10. I need to convert that to moles. The molar mass of butane is 58 grams in 1 mole of C4H10. And then I'm going to go, whatever, remember, whatever's up here comes down here, moles of C4H10 to moles of whatever they're asking me about, which is carbon dioxide. So I'm going to go to moles of CO2. From the balanced equation, 2 moles of butane makes 8 moles of CO2. And then 1 mole of CO2 has a molar mass from the periodic table of 44 grams. So 0.125 divided by 58 times 8 divided by 2 times 44 equals 0.379 grams of CO2. Okay, and that is all of number 2. Okay, let's go to number 3 now. Number 3 says N2 plus H2 makes NH3. Part A, write the complete balanced equation. So it's N2 plus H2 makes NH3. Here's 2 N's. Here there's only 1. So I'm going to put a 2 there. Here there's 2 hydrogens. Here there's 6 hydrogens. So I'm going to put a 3 right there. Okay, and now that is a balanced equation. Okay, part B says 32 grams of nitrogen reacts with 12.5 grams of hydrogen. So right away, I recognize this question as being a limiting reactant problem, partially because the next sentence says identify the limiting reactant. More importantly, though, is it tells me, it gives me an amount of nitrogen and an amount of hydrogen. So we know that we don't have an excess reactant. Okay, what we do, but we don't know what it is yet. So in order to calculate the limiting reactant, we're going to take one of our reactants. It doesn't matter which one. So I'm just going to choose 32 grams of N2, and I'm going to convert from grams of this one to grams of this one. So nitrogen has a molar mass of 28. There's 28 grams in 1 mole of N2. And then, just like what we were doing before, moles of N2 on the bottom, because that's what I have here, to moles of the other reactant on the top, which is H2. From the balanced equation, 1 mole of N2 reacts with 3 moles of H2, and then 1 mole of H2 has a molar mass of 2 grams. So 32 divided by 28 times 3 times 2 equals 6.86 grams of H2. Now remember, that means that if I start with 32 grams of N2, this is how much hydrogen I'm going to need to react with all of that. So this is how much hydrogen I need, that I need to compare that to how much hydrogen I actually have. According to the original question, it says it reacts with 12.5 grams of hydrogen. So I have 12.5 grams, but I only need 6.86. So I have plenty of hydrogen, which means hydrogen's not going to run out, which means that N2 is the limiting reactant. And again, explain my reasoning, because I need 6.86 grams of hydrogen, but I have 12.5 grams. Then that's enough of an explanation right there. Okay, part C. What mass of NH3 is produced in this reaction? So now they're asking about the product. How much of this are we going to get from this reaction? And well, remember we've got 2 numbers in part B. Which number do I use? Remember that I use the number from the limiting reactant. So I said that N2 is the limiting reactant. Okay, how much N2 do I have? I have 32 grams of it. So that is what I use to now answer the question about how much product I'm going to get. So there's 28 grams in 1 mole of N2, and then I'm going to go from moles of N2 to moles of whatever they're asking me about, which again in part C they're asking about NH3. So I'm going to convert to moles of NH3. And then from the balanced equation, 1 mole of N2 makes 2 moles of NH3. And again, they want to know mass. So now I've got to go to grams again. In 1 mole of NH3, 17 grams. So now I just go to my calculator. 32 divided by 28 times 2 times 17 equals 38.9 grams of NH3. Okay, and then part D, how many grams of the excess reactant is left over? Well, we got lucky on this because I only need 6.86 grams of hydrogen. I have 12.5 grams, so I know how much I have, and I know how much I'm going to need, 6.86. So I'm going to just take 12.5 minus 6.86, and that is 5.6. This only has 1 number after the decimal point, so does my answer. 5.6 grams is going to be left over. Now, the only reason I didn't have to do any math there is because I got lucky. Anytime you do a problem and you calculate this and that one ends up being the excess reactant, well, that makes your math on part D a lot easier. You can just take in the problem how much of that excess reactant you're given and then how much you're going to use up, and then just subtract them. If I had done it the other way, if I had started here with H2 and gotten N2, I still would have gotten N2 as the limiting reactant. However, then I would have had to have done this step down here, this whole thing, in order to figure out how much hydrogen we were going to use in this reaction. Question number 4 says H2O plus Li makes LiOH plus H2. Write a complete balanced equation. So H2O plus Li makes LiOH plus H2. So in this case now we've got 2 hydrogens, and on this side we have 3 hydrogens. So that's going to be a problem there. So we can put a 2 there. That makes 4 hydrogens. And then let me kind of clean that up there a little bit, plus H2. So now I have 4 hydrogens. So again, here I have 2, here I have 1. So if I put a 2 right there, remember that goes to everything. So that makes 2 hydrogens plus 2 more makes 4. And now that's 2 oxygens, and hey, there's 2 oxygens, and then 1 lithium, 2 lithiums. I put a 2 right there. And now that equation is balanced. Okay, part B, very similar to number 3. It gives you an amount of water, it gives you an amount of lithium. Identify the limiting reactant. So following what we just did in number 3, try to go ahead and pause the video at this point and try to follow what we did in number 3 and basically do the same thing here in number 4. Once you've tried that, then come back and just see how I did it. So again, I'm going to take, it doesn't matter which reactant I start with. I'm going to start with 22.4 grams of H2O. If you started with the 8.25 grams of lithium, that's fine. It doesn't matter. We're going to end up with the same limiting reactant anyway. There's 18 grams and 1 mole of water. From the balanced equation, we're going to go from moles of whatever's given to us to moles of whatever they're asking us about, which remember, when you're figuring out the limiting reactant, you go from one reactant to the other reactant. So 2 moles of H2O reacts with 2 moles of lithium, and then 1 mole of lithium has a molar mass of 6.9 grams. So 22.4 divided by 18 times 2 divided by 2 times 6.9 is 8.59 grams of lithium. Okay, now in the equation, so this again, this is how much lithium I need. I need 8.59 grams, but I only have 8.25 grams. Again, I'm just getting that from the problem. So I have 8.25, but I need almost 8.6. I don't have enough. And so that tells me that lithium is the limiting reactant. And again, how would I explain that? Just by my math right here. Because I need 8.59 grams of lithium, but I only have 8.25. Okay? Now in part C, remember, why do we figure out that limiting reactant? Because that's what we need to use to figure out the answer to how much product we're going to get. So what mass of lithium hydroxide, a product, is produced in this reaction? Well, I've got to use my limiting reactant. Now, I've got 2 numbers, though. I have 8.59 and 8.25. Which lithium do I use, the need or the have? Well, think about it. How much lithium could you use? What's the maximum amount of lithium that you could use is how much you have. So reading the original problem, I have 8.25 grams of lithium. Okay, so that's the number that I have to use. I don't actually have 8.59. Okay, remember, that's how much I would need to react with all that water. I don't have that. I have 8.25. So 8.25 grams of lithium. There's 6.9 grams in 1 mole of lithium. And then I'm going to go from moles of lithium to moles of, what are they asking me about in the question? Oh, they're asking me about LiOH. So I'm going to go to moles of LiOH. And then balanced equation, 2 lithiums, 2 lithium hydroxides. And then we're going to go 1 mole of lithium hydroxide has a molar mass of 6.9 plus 16 plus 1, which is 23.9 grams. So 8.25 divided by 6.9 times 2 divided by 2 times 23.9 is 28.6 grams of LiOH. Okay, and then the last part, D, how many grams of the excess reactants left over? Now, in this case, we are going to have to do some more math because, again, this part right here ended up being the limiting reactant. So now we need to figure out, based on how much lithium we have, how much H2O are we going to use. So I'm going to take 8.25 grams of Li, and now I want to go from here back to water. So 6.9 grams in 1 mole of lithium. I'm going to go from moles of lithium to moles of water, and it's a 2-to-2 ratio. And then 1 mole of water, 18 grams from the periodic table. 8.25 divided by 6.9 times 2 divided by 2 times 18 equals 21.5 grams of water is what I need. And then from the balanced equation, it says we have 22.4. So I'm going to take my 22.4, I'm going to subtract 21.5, and I get 0.9 grams of water, again, left over. Okay, number 5 says a 15-gram sample of an unknown compound containing carbon, hydrogen, and nitrogen is completely combusted in oxygen gas and analyzed by combustion analysis. Ugh. The sample produces 29.3 grams of carbon dioxide and 20.8 grams of water and an unknown amount of nitrogen. Find the empirical formula of the compound. So in a combustion analysis problem, your first step always is to take your grams of CO2 and your job is to get grams of carbon. And then the second thing is to take your grams of water and get grams of hydrogen. Once you know those two, we're going to add the two together, grams of carbon plus grams of hydrogen, and we're going to compare that to our total mass. So they say that there's 15 grams of this unknown compound. So those two added together, if it's less than 15, then we know something else is in there. And in this case, we know something else is in there because in the problem it says it contains carbon, hydrogen, and nitrogen. So we know that there's something else in there. We just don't know how much. So we've got to use this to figure this out. So I'm going to do that first part right here. I'm going to take 29.3 grams of CO2, and I'm going to go 44 grams in 1 mole of CO2, and then 1 mole of CO2 has 1 mole of carbon in it, and then 1 mole of carbon has a mass of 12 grams. So 29.3 divided by 44 times 1 divided by 1 just cancels, times 12 equals 7.99 grams of carbon. Okay, and then I'm going to do the same thing with the hydrogen, or the water. I'm going to take 20.8 grams of H2O. There's 18 grams in 1 mole of H2O. And then 1 mole of H2O has 2 moles of H. Again, that's where people mess up, is if you look at water, there's 2 hydrogens in water. That means for every 1 mole of water, there are 2 moles of hydrogen. And then 1 mole of H has a mass of 1 gram. So 20.8 divided by 18 times 2 equals 2.31 grams of hydrogen. So now, like before, we're going to add those two together. So 7.99 plus 2.31, 7.99 plus 2.31 equals 10.3 grams. And then they tell us at the beginning of the problem that it's a 15-gram sample. So if it total is 15 grams and 10.3 of those grams are carbon and hydrogen, 15 minus 10.3 is 4.7. Okay, and it's 4.7 grams of what? Well, again, it tells us it contains carbon, hydrogen, and nitrogen. So it's 4.7 grams of nitrogen. Okay, and now now that we've got all that mass accounted for, all 15 grams are accounted for, now we do the percent to mass, mass to moles, divide by small times till whole. So we're going to take 7.99 grams of carbon, 12 grams in 1 mole. 7.99 divided by 12 equals 0.6658 moles. And again, I'm not worried about significant figures. I'm worried about getting the right answer. And then 2.31 grams of hydrogen is, because it's 1, is 2.31 moles of hydrogen. And then 4.7 grams of N. There's 14 grams in 1 mole. 4.7 divided by 14 equals 0.3357 moles of N. Now that's our smallest number, so we're going to divide everything by 0.3357. So 0.6658 divided by 0.3357 equals really close to 2. So that's 2 carbons. 2.31 divided by 0.3357 equals, I don't like that number. It should be 7. Clearly, maybe one of my original numbers isn't quite perfect, but that should be really, really close to 7. And on your test, you're not going to have anything that's that far off from 7, but just to not waste more of your time, that should be 7. Okay, and then divide that by 0.3357, that equals 1N. So the formula comes out to be C2H7N. And again, that 6.88 that you got here, that will not happen to you on a test. I'll make sure that number is closer to a whole number. You would on a test, if you got 6.88, I would think that you messed up. But knowing that the answer was this beforehand, I know that clearly there's a number that's just a little bit off there. Okay, so that is part B, and then part C. Oh no, sorry, that was part A. Part B says the molecular formula is 135. So now we're going to take this whole thing and we're going to add up all the masses. So 12 times 2 is 24, plus 7, plus 1 nitrogen is 14. That equals 45. So this has a mass of 45. It's saying the molecular formula has a mass of 135. 135 divided by 45 equals 3. So that means I've got to multiply everything in that formula by 3. So that makes it C6H21N3. Okay, and then it says write the balanced equation for that combustion. So we've got C6H21N3 plus O2 makes CO2 and H2O. Now remember back in the original problem, it says, and an unknown amount of nitrogen gas, so N2 is also one of our products. Now right away we can see we've got an odd number, but we're going to need to have even numbers here. So right away I'm just going to double that, and that's going to give us even numbers. So 2 times 6 is 12. That's 12 carbons. 42 nitrogens means I've got to have 21 H2Os, and then 6 nitrogens means I need a 3 there. Okay, and now that gives me 24 oxygens plus 21. Uh-oh, I've got an odd number again. So I've got to come back to the beginning again, and I've got to double everything again. So that becomes a 4. This becomes a 24. That 21 becomes a 42. And the 3 becomes a 6. So now, let's count all total. 24 times 2 is 48. So there's 48 oxygens there. Plus, here we've got another 42. That equals 90 oxygens. So that means back over here, I need 45 O2s. And now that equation is balanced. Gross. Okay, last one, number 6. Says 42.6 grams of unknown compound. So basically just like number 5, but in number 6 it doesn't mention the nitrogen component at all. So it's some unknown compound. It could have just carbon and hydrogen in it. It might have carbon, hydrogen, and oxygen in it. Let's figure it out. So let's take our 120.15 grams of CO2. There's 44 grams. This is just like the other one. 1 mole of CO2, and 1 mole of CO2, there's 1 mole of carbon, and 1 mole of carbon, 12 grams. So 120.15 divided by 44 times 12 equals 32 77 grams of carbon. Okay, and then we've got 49.15 grams of water. That is 18 grams in 1 mole of water. And then again, this is where people make mistakes. 1 mole of water has 2 moles of H, and then 1 mole of H, 1 gram. So 49.15 divided by 18 times 2 equals 5.46 grams of H. So now I'm going to take the mass of the unknown compound, 42.6. I'm going to subtract the carbon. I'm going to subtract the hydrogen. 42.6 minus 32.77 minus 5.46 equals 4.37 grams left over, so that means that has to be oxygen. So now that I know my mass of each element, now I can, again, now I go to my percent to mass, mass to moles. So I've got 32.77 grams of carbon, 12 grams in 1 mole. 32.77 divided by 12 equals 2.73 moles of carbon. My moles of hydrogen are going to be 5.46 moles, not oxygen, that's hydrogen. And then for oxygen, I'm going to take 4.37 grams of O, 16 grams in 1 mole. 4.37 divided by 16 equals 0.273 moles of O. Obviously 0.273 is the smallest, so divide everything by 0.273. So that gets you 10 carbons. 5.46 divided by 0.273 equals 20 hydrogens and 1 oxygen. So my balancing, or my equation is C10H20O. Okay, and now the molar mass of that is 120 plus 20 plus 16 equals 140 is 156. Part B is telling me that the molecular formula is 312. 312 divided by 156 is 2, which means I've got to double everything in that formula. So it's C20H40O2. And then the very last thing I've got to do here is I've got to write the balanced equation. So C20H40O2 plus O2 makes CO2 and H2O. So 20 carbons, 40 hydrogens, means a 20 there because 20 times 2 is 40. And then all total on our product side, on our right side, we've got 20 times 2, there's 40 oxygens, plus another 20 equals 60 oxygens. So here we've got 2 already accounted for, so we need 58 more on this side, which means a 29 goes right there. And that's your review right there.